Okay, so for this episode, we got something really special. So the guest today is Craig Gidney, basically the creator of Quirk, the tool that you see here, right? Craig also runs Algorithmic Assertions, which is a blog where you have the actual Quirk link here, and then it's been one of the biggest inspirations for me, especially because the way that Craig writes, it really feels like you can kind of follow his thought process, and this is all what quantum intuition is for me as well, right? So it's kind of about sharing my thought process as I learn and as I try to solve things and I get stuck, etc. Right? And it's kind of at the end of the day also the spirit with the Turn the Qubits Off series, which is to kind of share someone else's way of thinking about a particular problem. So this time I asked Craig, because a regular puzzle will probably too easy for him. I asked Craig to solve a little bit of a more difficult task, which is fix this implementation of Grover's algorithm. So I basically built a Grover's algorithm that it's buggy, right? So it has a problem or a couple of problems in it, and then the challenge is figure out what happens, what's going wrong, and fix it. With a couple of set of rules that you'll see now in the video as I switch to his reply. It's been, I'm not going to do a step by step. I'm just going to leave you guys with the video because I think it's just a mind gold of, or gold mine of, knowledge, and I think just the rawness in which and the way in which Craig thinks about it is just crazy. And I'll probably do a follow-up where I really kind of break down the way he approached the problem, because I think there's a lot to learn about it. And he even fixed some of the stuff that was not supposed to be fixed, but you'll see that. Okay, so I'm going to leave you now with a solution from Craig, and I hope that you enjoy it. I hope you enjoy it. I mean, really, at that point, kind of crossing 1,000 subscribers was also a bit of a milestone for me, and I'm kind of feeling excited about the message and kind of about the spirit of the channel, and I really want to continue these. And in the next couple of days, I'm going to be releasing a couple of other things around puzzles and around building up intuition, which I think that and I hope you guys are going to like. So yeah, I'm not going to steal too more of your time. Here's Craig. Enjoy.
All right. So recently, this person who makes a YouTube channel about learning quantum computing sent me a puzzle to solve. And apparently it's about fixing a broken Grover search that's supposed to recognize inputs that have exactly 2 bits set. So I'm going to go look at this puzzle and see if I can solve it. All right, so this puzzle is encoded into a tool that I made called Quirk, and I'm quite happy to see that almost all of the toolboxes are available for use, since otherwise I'd be pretty constrained. Okay, so what do we have here? We have this one box, which is probably the oracle for counting the number of 2s, and then we have this double A box. So I think the first thing to do is to try to figure out what these boxes are actually doing. And the easiest way to do that is to get a look at their matrices by using something called the state channel duality, where we set up a bunch of entangled qubits, operate on the entangled qubits, and then because of a nice coincidence in how Quirk displays states, we get basically a visualization of the matrix. So I look at this matrix and I immediately see that it looks like most of the things are about the same size, and there's kind of this diagonal that's different. So I think that this is what the Grover diffusion operation looks like. So a diffusion operation will typically look something, for reference, like this. Yeah, so you can see that those look basically identical. And if I repeat this and that, you can see that they're exactly undoing each other, and this is a self-inverse operation. So that's what this AA is. It's exactly this gate. The other thing to try to figure out is this count gate. This one is a little trickier maybe because it looks like it's going to produce output that's not being uncomputed. So it could just be that the issue is that the count has to be repeated. Anyways, let's try the same thing with this, but I don't quite have enough room to work with here. All right, let's get this out of the way temporarily and get that out of the way. And move this down too. And apparently the output is going onto those two. So this particular pattern that was back here where you had a 1-bit set and you're applying a controlled Z is completely equivalent to just having the Z as replacing one of these controls with the Z. Like the 1 is completely irrelevant to that. Anyway, so apparently I'm supposed to do that. And then I'm guessing that this is, okay, it is not self-inverse. Oh, right. Okay. I need to, so currently the trouble that I'm having is the fact that I have these 2 extra bits that I don't want to have to care about that are right in the middle of my state display. So I'm going to move them out of the way like this, and then shrink the display a little bit. And we can see that that's still not quite right. When I've got these in the wrong order. Okay, so what we can see now is that we have this diagonal. So whatever this is doing, it's only applying phasing gates. Like this is the right shape. We're just seeing that it's somehow become entangled with these things. And we can see the nature of that by conditioning on this bottom qubit. So I'm going to condition one way and condition the other way. So clearly what's going wrong is that this is not actually a self-inverse operation the way that I thought it was. So what can we try instead of that? Let's go back to the initial state by holding undo. And let's look a little bit more closely at how this count reacts to different inputs. So if I have one of these that's on, I can see that that's on. And if I have 2 of them that's on, I see that that's counting correctly. And 3 of them, that's also good. And if all 4 are on, then that's also looking fine. It seems like, oh, I think all I have to do is I have to uncompute the count instead of trying to repeat the count. All right, sorry if there's a little bit of a hitch in the video. I'm using a trial version of the screen recording software that only lets me do 5 minutes at a time. Anyways, so it looks like depending on the number of things that are set here, it is giving the correct output. Like I can see that this is off and this is on when there's exactly 2 here. So that part is good. And all I need to do is to do the second part of it where it gets rid of this intermediate state in order to basically uncompute the intermediate garbage that we've made. So all I have to do is I have to implement this count in reverse. And that's actually quite simple. I just uncount. And then I can probably just repeat these steps in order to perform the diffusion. Except looking at this, I can see that it's still not quite right. And probably the easiest way to check that I'm actually uncomputing this the way that I think that I am is to see if I can feed in states that are changing in incorrect ways. So what I'm going to do is I'm going to apply this cycling effect here, which is cycling through all the inputs. And this is supposed to do something, and this is supposed to do exactly the opposite. And then, so at this point, we should be back to the normal count. And actually, it does look like this is working. Although it could be that there's some hidden phase present. So it could be that there's some phase kickback occurring. And that's probably why this doesn't look right. And the way that we have to see that is by doing that state channel duality thing again. So let's get rid of this for a second. And let's get our state channel duality bit back. And okay. Set up entanglement between the 2 things. I still don't have enough room. All right, I'll just bring this stuff back later when I need it. Myself some more room. Okay, Although actually looking at this, all of the little arrows are pointing to the right, and I'm betting if I uncompute it that it's also going to be exactly what it's supposed to be. Oh, I just got that slightly too low. Oh, so I do actually have the inverse here. All right. Let's back up again. Huh. So there's something else that's broken. Is it the diffusion? Oh. Right. So earlier I showed you the example of what the diffusion operation was doing, which was this operation here, this one right here. So the thing about this is that this inverts the state where all the qubits are in the minus state. This initial state is set up to prepare all the qubits into the plus state, and the state that you're inverting has to match the initial state. So what I did here is I just applied these x's in order to get the qubits into the minus state. It's maybe a little bit clearer if I just directly show that it's like that. So you can see here that the states that are being amplified, the ones that have little extra green bits here, are the ones that have exactly 2 1s inside of the little display that's showing here, which is a little hard for me to show with my mouse because it goes away when I move towards it. And if I instead use plus, it doesn't work. Anyways, so that fixes it. And then we just have to iterate a few times. So we're going to apply our oracle again. Because there's so many solutions, because there's so many solutions compared to the non-solutions, we're actually pretty far into the regime where Grover is going to step too far. So we actually need to lower the amount that it's rotating. So we can do that like this, and we can see, oh, it might actually need even less than 1 step. Let's see if this goes to exactly 0 as the angle changes. And it stops at about 1. Okay. Does this one go to exactly 0 then as the angle changes? Does it go too far? Okay. This might be tricky. Okay, so this is a little bit tricky. Oh, I know what the issue is. The issue is that this diffusion operation also has to be at an angle. Yeah, that's exactly what it is. Okay, let's see if we can find a way to get it kind of just right. So let's just try a number 0.1. That's 2%, and then if I change it to 0.2, and the leftover is 3%, so it looks like that got a little worse, so maybe I should go down instead. Or I should just be trying completely other numbers. It seems like any amount that I rotate is actually making it worse. So it could be that we overshot with the first step, and I should actually go backwards. So I'm not actually allowed to remove this gate, but I can make it go backwards from here instead of removing it. Oh no, that also doesn't seem to do it. And it's getting kind of annoying for me to constantly change these angles manually. So I'm going to switch to these parameterized versions, which can be controlled by an input that's elsewhere in the circuit, and then count through it like this and just see if, okay. It looks like it just gradually gets worse. Like it starts off at about 14%, and then this is actually, the chance of getting the right answer is actually going down over time. So I'm clearly over rotating, which makes me think that I actually need to apply this over here, and I need to break the rule that I'm not allowed to change this a little bit. I guess I'll just cancel it out and then do my own thing. Get rid of this second part. Okay, let's see if we pass through 0. Yes, we do pass through 0. And when are we passing through 0? So it's roughly around half of the way down. So about here. Yeah. And then we can kind of dial, oh, that looks really good. All right, there we go. So this angle is roughly a half, maybe, or maybe that's a quarter, plus an eighth. So this would be a half plus an eighth, I think. And then I do the same thing here. Yeah. Okay, there we go. It's actually fixed now. So the things that I fixed were, first of all, the input state didn't agree with the diffusion step that was being applied. And secondly, because there were so many solutions, it was over-rotating compared to what it should have been. So I decreased the angle of rotation, although I might have kind of cheated by having to cancel this out. And thirdly, it wasn't uncomputing this intermediate garbage here, which I uncomputed by doing this. And I guess that solves it.